In this video, we're going to look at some periodic table trends. Firstly, we're going to look at atomic radius. Secondly, we'll look at ionization energy. And then lastly, we're going to look at electron affinity. Now, throughout this video, there's going to be a bunch of slides with a lot of information. I'm not going to be reading off the information verbatim. If you'd like to pause the video to perhaps take some notes or just to read over the slides, I'd recommend doing that. So let's take a look at some Bohr-Rutherford diagrams. And so if you were to draw diagrams of the first 18 elements in this case, it becomes pretty obvious when we're looking at the size of an atom that as you go down a group, well, they tend to get bigger. There's more electron shells. As we go across a period, though, the pattern is less obvious. They all kind of look the same. That's because we sort of draw them the same, but there are some differences. So let's investigate. So atomic radius, like I said, as you go down the group, they tend to get bigger. As we actually go across a period, the atoms are actually going to be getting smaller in size. So I've got a picture here to put this into perspective. So there's a picture of our periodic table. Radiuses are listed in angstroms. Again, it's pretty clear what's going on here, that our biggest atoms are generally going to be found down in this area over here. So let's take a quick look here and some reasons about why our atoms are getting bigger. It's really a couple of things going on. We're adding more electrons. These electrons are repelling themselves, and so they're pushing out further from the nucleus. So our trend going down a group is going to be that as you go down a group, atoms get larger because we're adding extra electron shells. Now, there is a second reason. So we've got some valence electrons that are actually being shielded by the pull of the positive nucleus. I like to call this the shielding effect. All those inner electrons are in the way of the outer electrons. So those outer electrons are not feeling the full pull of the big positive nucleus. So as we go down a group, our atoms are getting larger because we're adding extra shells, and we got this shielding effect, and there's repulsion going on amongst those electrons. So there's really a couple of different reasons. So for atomic radius, going across a period, now we got to think about this. As we go across a period, we're not adding any more shells. What we're adding is these giant protons and little tiny electrons. So the big positive protons have more effect on the overall size of the atom than just adding these little electrons that are repelling each other. So as we're actually going across a group, or sorry, as we're going across a period, these elements are getting smaller. So as you go across a period, the size of an atom will decrease, and this is because we're not adding any more shells. We're just adding giant protons that are pulling in those outer electrons better. A couple of example problems here. So I've got three sets of elements. You can pause the video right now, and I want you to write down or decide which is going to be the largest, which is going to be the smallest. Okay, so for our solutions here, largest to smallest, all of these atoms were in the same period, so we're looking at the one furthest to the left, which is going to be boron. For B, they're all in the same group. We're looking for the one furthest down the group. That's going to be potassium. And none of these are in the same group or period, so we're just generally looking for the one that's in the bottom left corner, closest to francium or cesium on the diagonal, and that's going to be gallium. Okay, next part of this video, we're going to look at ionization energy. So our definition is going to be the energy required to remove the outermost or an outermost electron from an atom. So this could be like a valence electron. So this is going to depend on the size of an atom. If an atom is really big, it's going to be easy to take an electron away. If an atom is really small, it's going to be a lot more difficult to take that electron away. It's almost like that atom's going to put up a big fight to keep an electron if there's only a couple of them. But if an atom has a lot of electrons, it might not fight so hard. And that's going to be the amount of energy. That's how we're going to measure this. So the larger an atom, the easier it's going to be for us to pull away an electron. So we're not going to need much energy. We're going to have a low ionization energy. So going down a group, now we have to relate this back to size. We know as we go down a group, atoms get larger. So the larger an atom, the easier it is for us to take an electron away. So ionization energy is going to decrease down a group. So it's the exact opposite of our atomic radius trend. And so here is our trend, our summary. As you go down a group, ionization energy decreases. So what about across a period? Well, we already know that as you go across a period, atoms get smaller. So it's going to take more energy for us to take away an electron. And so ionization energy should increase as we go across a period. So our trend is, as you go across a period, atoms get smaller, and so it's harder to remove an electron. It takes more energy. We have a higher ionization energy. And here's a picture to represent that general trend. Got some example problems here. You always got to be careful when you get a problem. What exactly is the problem asking? Highest to lowest, lowest to highest. You need to be clear. So we've got we've got a couple of questions here. You can pause the video and decide which is going to be the highest and which is going to require the least energy. Here's our solutions, all based on our size. So our smallest atoms should take the most energy to remove an electron. Let's look at our third trend, electron affinity. So this was kind of the opposite of ionization energy. In ionization energy, we were taking away electron. Now we're going to add an electron. So what happens with this one, though, is when you add an electron, that electron is going to interact with the atom, and there's going to be some energy released. And that's the actual thing we're going to be measuring here. So the amount of energy released depends on how well the electron can interact with the nucleus. So what I'm saying here is if we have a small atom, that added electron is going to get really close to the nucleus. There's going to be a big interaction. There's going to be a big energy release. So as we go down a group, the size of atoms increase. Therefore, as size increases, our ionization will decrease. It's again the exact opposite of our atomic radius trend, and it should follow the same as our ionization energy trend. And so we've learned already that as you go across a period, atoms are going to get smaller. So that means we're going to have more energy released when we add in that electron. So electron affinity will increase. There's a picture. And lastly, a little summary here. You'll notice that my arrows are indicating which direction increasing is going to be. Ionization and electron affinity, their trends are depending on atomic radius. So if you put that little picture in your mind, that might help you answer some questions. Now, if you ever have to write some answers, here's a couple of tips. If you're doing an answer on atomic radius and it's something about a group, you want to talk about adding electron shells. You want to talk about the shielding. If you're going across a period, you want to mention something about the giant positive nucleus. If you've got a question dealing with ionization energy and electron affinity, you always want to reference the size of the atom. Hopefully this video gave you a little insight into this topic. Thank you very much.